Morning, folks. Okay, we didn't finish determinants last time, so I'm going to wrap up that discussion, and then we'll move right into the eigenvalue, eigenvector story. And hopefully by next Tuesday, I'll be done with what I needed to cover, and Vladimir will take over with circuits. I want to remind you that those of you who are even considering possibly dropping the class should not do so until you take the quiz. And even though it's part of the homework, and it's due, I think, sometime next week. I don't know exactly till when they extended it. You probably want to take it no later than tonight or maybe tomorrow morning to see where you stand with the class. We'll release the solutions tomorrow sometime. Okay? Actually, no, we won't release the solutions tomorrow because you have to do it by homework. I take that back. Okay, so there were three axioms that so remember we said that the determinant of A is a function that takes a square matrix and maps it to a real number. If you find a function that has the following three properties, you have stumbled upon the determinant because there is, in fact, one and only one function associated with a matrix that satisfies these three properties. One of them is that if the matrix is the identity, then its determinant is 1. The second property is that if and I'm going to illustrate this again in the case of 2 by 2 matrices. So if I scale the one row of this matrix by a scalar t, that scalar just pops out. And you're left with t times the determinant of the original matrix. So that's the second property. And the third property is that if I add to any row some vector, this would be b prime, and I keep all other rows the same. So I take, in this case, the first row and add to it a row vector. I don't care where that row vector comes from. As long as I add a vector to the first row, in this case, that determinant is equal to the original determinant plus the determinant of the matrix whose first row is the row that I added to the original matrix, and all other rows are the same. So any function that satisfies these three properties is the determinant function for that matrix. Okay, then I said that we can derive a whole bunch of these other properties of the determinant from these three basic axioms. And one property that we talked about that I'll just go over quickly. I forget about numbering them. I'll just write them as bullets. A row exchange reverses the sign of the determinant. Reverses the sign of determinant of A. And basically, it means that if I have a matrix A, B, C, C, D. Wait a minute. I missed one. This was actually property 3. This was property 2, axiom 2. I'm sorry. I know why I messed up. So this is actually axiom 2. I think I wrote it as axiom 2 before. This is 3A, 3B. So the function has to satisfy these two and this one. Basically, it means that if I exchange the rows, I reverse the sign of the determinant. Okay, so let me do a rewind. If a function that you stumble upon satisfies the property that if you stick the matrix, the identity matrix, into that function, you get 1. And if you scale a row by some factor t, that function gets scaled by the same factor t. And if you take the matrix whose determinant you're trying to find, and you keep all the rows the same, I don't care which row you pick to modify, but you keep all the rows the same except one, and add to that one row vector an additional row vector, in this case A prime B prime, then the determinant will be the sum of the original matrix plus the original matrix where the row that you modified is taken out and the row that you added is inserted. If you do that, the determinant of the modified matrix is the sum of these two. So this is sometimes called the multilinearity property. Multilinearity property. Multilinearity is essentially linearity when you have a function that has multiple inputs. In this case, the determinant function is linear with respect to every single row. So if you think of the determinant function as the function of all the rows of the matrix A, sometimes in some textbooks you'll see that this is written as the function of the first row, second row, and so on, row vectors. How many do I have? N. Sometimes it's written this way. So it's linear in each of these individual ones. And if you want to be clear, since I promised you I'll put a transpose on all the rows, I'll put it that way. So basically, if you do a linear operation on any of these variables, the determinant function will exhibit linearity property with respect to that particular component of the function. And that's what multilinearity means. And if you have a row exchange, then you simply reverse the sign. Okay? So any function that satisfies these properties will be your determinant function. Okay. Now, we start working our way out based on these and derive some other properties. So one of the things I talked about was if A has two equal rows, then the determinant of A equals 0. And I'm going to display that in this way. So I'm going to write one row as AB, and I'm going to write another row as AB, but with a different color. So I do a row exchange. What happens if I do a row exchange? I'm looking at, where does the white row go? The bottom. And the top row, the green row, goes to the top. Are these two matrices different? No, they're the same. So this, on the one hand, this determinant must equal the determinant of the original matrix because I haven't changed anything. On the other hand, this property 2 says, so I'm going to put 2, says that this should be equal to minus the determinant of the original matrix. Okay? The only way a scalar can be equal to its negative is what? Is if the scalar is 0. So these two must be equal. And must equal 0. Question?
Does this property apply to matrices bigger than 2 by 4?
Yes. Pretty much everything I say applies to all higher dimensions. Yeah. Okay. This one you should be able to see easily, right? That regardless of what the size of the matrix is, when you exchange two rows, you get the same matrix back. So the determinant should not change. But the row exchange property says the determinant should reverse sign. So the only way that that can happen is if the determinant is 0. Okay. The other thing you should notice is that if two rows of a matrix are equal, then what does that say about the invertibility of that matrix? Is it invertible? No. So you're beginning to get a sense of matrices that are not invertible, or matrices that are singular, having determinant equal to 0. In fact, it turns out that a matrix is non-invertible, or a matrix is singular, if and only if its determinant is 0. And you'll see this pattern arising. I won't prove that result, but that's a true statement. Jack, you had it. Okay. Yeah. Okay, let's go to the next property. What do I want to discuss? So if I have a matrix where one row is a scalar multiple of the other row. So one row is AB, the other row is simply T times that row. Then what should this determinant be? Why? What do I do with the T? Take it out. By what property? Give me the number. 3A. By 3A, this is T, A, B, A, B. And then this, you know, is equal to 0 because of what we just showed. Equals 0 by previous property. And let's go to another property. If I have a matrix AB and I add to one of the rows some multiple of another row. So I take the first row, multiply it by T, and add it to the second row. What do you think I should get? Why? Take me step by step. What do I do to the TA addition? Which property do I invoke? 3B. And if I invoke 3B, this should be the sum of two determinants. The first one is AB, CD, and the second one is AB, louder, TA, TB. And what do you know about this one? It's 0. So you get the original determinant back. Notice I'm going through properties that are related to the kinds of operations that you've been performing for several weeks now on matrices, which is linear combinations of rows. So here we have, so we've talked about scaling of a row. Now we've talked about the addition of a row. Now we're talking about taking linear combinations of rows. So I've taken one row, multiplied by some scalar t, and added it to another row, and the determinant doesn't change. And this is all good news, because as you perform these Gaussian elimination and Gauss-Jordan operations, it means the determinant is not changing as you're multiplying the matrix of interest with the elementary matrices. Because all of those, each one of those operations involves taking some kind of linear combinations of rows. So that's why we're going through some of these properties. Okay. I think I may have done this out of sequence last time. If a matrix has a row of zeros, what is that determinant? Why? I take out 0, and this can be any determinant, right? Whatever the determinant, I can write 0 as 0 times some even non-zero constant a, and I can write this 0 as 0 times some non-zero constant b, and whatever this determinant is, when I multiply it by 0, I get 0. Again, we go back to the point I made earlier, which is that a matrix has determinant 0 if and only if it is non-invertible. And you know that this matrix is not invertible, 0, 0, CD, because the zero vector can never be part of a linearly independent set of vectors. So I have row rank deficiency in this matrix. There's only one linearly independent row in this matrix 0, 0, CD. Okay. What else? I did that. Now we're getting warmer. the determinant of a diagonal matrix. Let's use just the first diagonal entry, second diagonal entry, third diagonal entry. So everything is 0 except the diagonal entries. What do you think this will be? Let me give you a hint, and I'll give you about 30 seconds to talk to your neighbors and see if you can sort this out. Start with an identity matrix, and step by step, modify that identity matrix to get this diagonal matrix. So if you start with the identity, 1, 1, 1. In the first step, what would you do to get a D1 in this entry? What would you do to this diagonal matrix? Multiply the first row by D1. So this would be D1, then the D1 by the property 2A comes out, and it would be D1 times the determinant of the identity, and you know that the determinant of the identity is 1, so this is D1. Now you take this matrix and you try to insert D2. What do you do to this matrix to get the D2 in the right place? Multiply row 2. So multiply, here I'll say multiply row 1 of I by D1. Now I do the same thing with row 2. Multiply row 2 of I by D2. And then I'll get D1, D2, 1's everywhere else. And this will be, then what do I do with this D2? It comes out. So it's D2 times the determinant of this. But this is D1. So I get, so let me write it explicitly. This is D1, 1, and that's a determinant. And so I have D1, D2. And if you continue in this way all the way to Dn, what do you think the answer will be? The product of all these diagonal entries. Dn. Okay, so anytime you have a diagonal matrix, the determinant of that matrix is very easily identifiable. It's simply the product of the diagonal entries. Now, if one of these diagonal entries is 0, what does that say about the matrix? It has a determinant of 0. What do you know about the invertibility of that matrix? It's not invertible because there is a 0 pivot, or a 0 row, or a 0 column. Whichever way you look at it, you get the same thing. If one of these entries, let's say D1, is 0, that means the first row is all zeros. So the matrix is row rank deficient. In fact, the first column will also be all zeros. It's column rank deficient, and the matrix is not invertible. And again, we have a situation where, a diagonal matrix is invertible if and only if all the di's are non-zero. If even a single one of them is 0, the matrix is not invertible. Okay. So what do you think the next natural category of matrices is? Pardon me. After the diagonal. Triangular. So what if I'm looking at the determinant of a matrix that has diagonal entries D1 through Dn? This side is all zeros, and this side is I don't know and I don't care. E-I-E-I-O. What do you think will happen in this case based on the properties that we've gone over? Any guesses? It's the same. Why? Well, I'll give you a hint. I don't know and I don't care, but why is it that I don't know and I don't care? Can I convert this into a diagonal matrix? By what kinds of operations? Pardon me? Say it in terms of stuff that we've done today. Scaling a row and adding it to another row, right? If I want to get rid of the entry right above this dn, what do? I scale this last row by something, some appropriate number, and I add it to the next row up, and I get rid of the off-diagonal entry there. And I keep doing this until I eliminate all of the stuff above the diagonal. And each and every single one of those operations that I do, those linear combinations, will do what to the determinant? Absolutely nothing. Did you have a question, Jack?
Yeah. Can something be invertible if it is not a basis?
What do you mean? So you're talking about the something, you mean the matrix?
Yeah.
So if a matrix is invertible, then its columns must form a basis for, if we're talking about square matrices here, then its columns must form a basis for Rn, yeah. Okay, so triangular matrices, and by the way, it doesn't matter if it's upper triangular or lower triangular. I can do the same operation, some linear combination of rows to get rid of every single off-diagonal entry. In the case of an upper triangular matrix, what you do is what you did in Gauss-Jordan elimination, which is just get rid of all these entries above the diagonal. So again, an upper triangular matrix is invertible if and only if the diagonal entries are non-zero. Cool. What else do I want to talk about? And okay, so let's do a 2x2 case. So I have A, B, C, D, and I'm trying to figure out the determinant of this. Okay? What is this determinant? I need a new chalk. What is this determinant? Well, how do I convert? Can I convert this into an upper triangular matrix? What can I do? Okay. That's kind of like saying eat healthy. Tell me the specifics. What should I eat? How do I get rid of the C? Whatever operation I perform gets rid of the C, correct? What is that operation? Multiply row 1 by C, and I subtract A times row 2. So what do I get here? Work with your neighbors and tell me what to put in this entry right here. And once I have that, I have my upper triangular matrix, and I can read off the determinant. So tell me what goes here. No, not the final answer. I want this entry here. Let's pick somebody. Neil, can you pick somebody? Do you need time to talk to each other? Why don't you talk to each other for about 30 seconds or so and tell me what entry goes here? What is it that I did to get this to be 0? Okay. Ready? You are? What's your name? Amy. Amy, go for it, Amy. Good. Speak loudly.
So what we said was that would be CB times AD.
C. So what is this? What do I subtract from row 2? What multiple of row 1? What do I have to multiply A by to get negative C, basically? C over A. So this is C over A times row 1. So I have to do the same thing here, right? So D minus C over A times B. So what is the determinant of this matrix? By the way, what happens if A is 0? What if A is 0? They pay me to be the devil's advocate. Switch the rows. And you already have an upper triangular matrix, right? If A is 0, you switch the rows, you have an upper triangular matrix, and you know the determinant of that, and you just multiply it by -1, you've got the determinant of the original matrix. Okay, so the determinant of this then, which is the determinant. Now, when I perform this operation, did I change the determinant? No. So the determinant of A, B, C, D is the determinant of A, B, 0, D minus, well, why don't we simplify this? So I have AD minus BC over A. Huh? Which is what? The product of the diagonals. It's the product of A and AD minus BC over A. These two cancel, and you get the famous formula for the determinant of 2 by 2 matrices. A, B, C, D is AD minus BC. I defined this a few lectures ago, and I postponed a more detailed discussion to later. This is that later. Any questions on what we've done? Okay, we'll chug along. The next property is if I take the determinant of T times a matrix, so basically if I take each row and multiply it by T, I take the next row, I multiply it by T. This is how I can view it, right? What should I get? If I keep all the rows to be the original ones, and I multiply the first one by T, I get T times the original one. Then I modify the second row with a multiplication. I scale the second row. What do I get? T squared, another T. So when I'm done with all this, I get T to the n, the determinant of A. Okay? All right. Now this is a tricky one. The determinant of the product of two matrices is the product of the determinants. If you look at different books, they'll have different proofs. But I've only found one proof that's spiffy, and that's in Gil Strang's book. First of all, if one or both of A and B are non-singular, let's say A is is singular, meaning if one of them, at least one of them, is non-invertible, does this equality hold? If A, B, or both are singular, then does this hold true? What's on the right-hand side? Let's say A is singular. What's on the right-hand side? 0. If A is singular, can AB be non-singular? Can you multiply a non-invertible matrix with, let's say, an invertible matrix? Let's say B is invertible, A is not invertible. If I perform that product, am I going to get an invertible matrix? Why not? If AB, if the product is invertible, the inverse is what? B inverse times A inverse. But if A inverse doesn't exist, the product doesn't have an inverse. Right? Recall, AB inverse is B inverse, A inverse. If A inverse doesn't exist, AB inverse can't exist. Another way to look at it is that if A is not invertible, its rows are linearly dependent, which means that I can multiply A by some matrix, by some row vector y to get the row vector 0 for some non-zero y. And this means that I can multiply on the right side by B, and I again get 0, which means the matrix AB has a non-trivial left null space, which means the rows of AB are linearly dependent. So if either one of the, and I can do the same argument if B is singular and A is non-singular. So this result is true. This identity is true if one of them is singular. If they're not, if they're both invertible, that's the more interesting case. If A, B are invertible, in other words, these exist, then I can define the following function. I'm going to define a function of the matrix A, which is the determinant of AB, whatever it is, divided by the determinant of B. In other words, I fix B, and I look at this ratio as a function of A. If this function, I'm not going to go through all the steps. I'm going to show you a couple of the steps, and then I'll leave it for you to convince yourself that the last property holds. If f of A satisfies, do you agree that this is a scalar function? With some determinant over some determinant. It's a scalar function. The denominator is not 0 because B is invertible. So if this satisfies the three principal axioms, then f of A must be what? The determinant of A. And if I can show that this is the determinant of A, it means I've shown that the determinant of A is the determinant of the product times the determinant of B, which proves my result. Okay? So the trick is actually to show that this function that I've defined in the following way actually satisfies the axioms. So does it? If I let A be the identity, do I get f of I equals 1? Yeah, because f of identity is the determinant of the identity times B divided by the determinant of B. The identity times B is simply B. So this is the determinant of B over the determinant of B, and that's 1. So the first axiom holds. What happens if I scale? So let's define C as the product of these two matrices. What if I scale one row of the matrix C? What is the nth row of the matrix C? If this is the nth row of C, can you tell me how it relates to the nth row of A? See, I told you that you need to be very quick with these matrix vector multiplications. if I look at this in terms of its rows, and I multiply it by B, what is the nth row of the product? Isn't it the nth row of A times B? Okay. So if I scale the nth row of A, what happens to the nth row of C, the product? It gets scaled. Now, if I plug it into this function, do I get T times f of A? So let's say A hat is A with its nth row scaled by T. What happens? What is the determinant of A hat? What happens in the numerator? That's the matrix C, right? The determinant of the matrix C. And I've scaled one of its rows, the nth row. So what do I get in the top? T times what? Determinant of AB over the determinant of B, which is T times the original function. So property 2A is property 3A is satisfied. And you can do something similar for the additivity. The main trick, is that you recognize the relationship between the rows of a product of two matrices and the rows of the first matrix in that product. That's the key to understanding what this function is doing. So anyway, you can try additivity on your own. Try additivity on your own. And you'll see that it satisfies that. And if you do the row exchange, if you exchange two rows of A, what happens to the two rows of the matrix C? If I exchange two of these rows, what happens to the corresponding rows in C? They're exchanged. So the determinant is negated. So the numerator of that property, the numerator there, is negated. So the row exchange property holds. It's not very complicated. What I really want you to focus on, actually, is the result. The result is very important. Determinant of a product is the product of the determinants. That's not true for addition. The determinant of a sum is not the sum of the determinants. So if the determinant of a product is the product of the determinants, can you tell me what the determinant of the inverse of an invertible matrix is? Talk to your neighbor. How is a matrix related to its inverse? When you multiply them, what do you get? While you do that, I erase some boards. Amy, you get to pick the next person. You've been selected. No, your neighbor. You are? Jesse. Go for it, Jesse. What do you know about A and A inverse? When you multiply them, what do you get? The identity matrix. So when you take the determinant of A inverse A, what do you get? the determinant of the identity, which is 1. And what do you know about the product of the determinant, or the determinant of the product? What did we just say? A little louder. I can't hear you even. A inverse times the determinant of A is equal to 1. So what does that say about the determinant of A inverse? In relation to the determinant of A. If the product of these two is 1, then what's this one? 1 over the determinant of A. And of course, you can't do 1 over the determinant unless that determinant is non-zero. But we said A is invertible, so its determinant is guaranteed to be non-zero. So for any invertible matrix A, the determinant of the inverse is simply 1 over the determinant of that matrix. Okay, we can go on and on and on about these properties, but I think I've covered what I needed to cover enough for our discussion on eigenvalues and eigenvectors. So if there are questions, ask now. Otherwise, I'll give you a 2-minute break, and then we'll start our eigenanalysis. Any questions on what we've done? This is one good exercise in going from first principles and deriving a whole bunch of things. Some of you who've taken Math 54 probably were drowned in cofactors and submatrices and so on. And it probably camouflaged some of these beautiful properties of determinants. But you don't need to go through all that grunge work to infer these properties. So go over them on your own time. All right, I'll give you 2 minutes, and then we'll start eigenanalysis. Okay. I lied. There is one property I still need before I move on to eigenvectors and eigenvalues. And that property is that the determinant of the transpose of a matrix is the determinant of the matrix itself. And again, this has complicated proofs in various books. If you go by what we did last time, which is the LU decomposition of a matrix, then so this was lower triangular with 1s on the diagonal, the main diagonal. And this was upper triangular. And it contained the diagonal elements were the pivots, right? So A transpose is what? What's the transpose of a product? What do you do to the order? Switch the order and transpose each. So L, which used to be lower triangular, now has become L transpose, which is upper triangular. And U, which was upper triangular, now is lower triangular. When you look at the determinant of A transpose, you're looking at the determinant of U transpose and the determinant of L transpose, right, by the product property. What is the determinant of L transpose or the determinant of L? Oh, the diagonal entries multiplied. But what are the diagonal entries for the L matrix? 1s. So this is all 1. Okay? The L matrix only had 1s on the diagonal. So its determinant is just the product of those diagonal entries, which is 1. And U is simply the product of, or U transpose, the pivots. But the determinant of A is also the product of the determinant of U and the determinant of L. This is 1. And the determinant of U is the product of product of what? The pivots. So they're equal. They're the same. So the determinant of a transpose of a matrix is the same as the determinant of the matrix itself. We'll need this when we get to the eigenanalysis. All right, let's start with our eigenvalue eigenvector story. I'm going to go back to our PageRank problem that we solved. Let's see, the diagram was, so eigenvalues and eigenvectors. Our PageRank problem had 4 nodes, 1, 2, 3, 4, and let's see, what were there was 1/3 here, 1/3 here, 1/3 down here. This guy went up by 1/2 and gave this guy a half, and then this guy gave 1 3 edges, links, so this is a half, and this is a half. So this was our, our graph. The connectivity matrix was 0, 1/3, 1/3, 1/3, and then for 2 it goes to 3 and 4. So these are 0. 3 only goes to 1, and 4 goes to 3 and 1. So this was our A matrix, and we had this dynamic equation, the time evolution equation, which governed how the people, if the state vector S represents the fraction of the population at each node, or its components represent the corresponding node population, then this would be the dynamic equation. We said that one way to look at the score vector is to think of it as the equilibrium state, namely the state such that if you enter it, you never leave it. So once you enter the equilibrium state at time n, or if you start off at time 0 in the equilibrium state, you will never leave it. And that led us to this equation. Okay? I never called this equation an eigenvector eigenvalue equation, but this is in fact, well actually I may have, but asked you to postpone that terminology till later. But this is an example of an eigenvalue eigenvector equation. The vector S star, the equilibrium state, has a very special relationship with the matrix A. When I multiply the vector S star, it doesn't change in this case. It's scaled by the number 1. It doesn't change direction. So S star, we say, is an eigenvector of A. An eigenvector is a vector that when you multiply it by the matrix, you get some scaled version of that eigenvector, of that vector. So more generally, you get more white chalk. In general, we say a vector V is an eigenvector of the matrix A if this relationship holds for some lambda in R. And V has to be the non-zero vector. So the zero vector can never be an eigenvector of any matrix, because anytime you multiply a matrix by the zero vector, you get the zero vector itself. So it's trivially true, this equation. So whenever we talk about eigenvectors, we're talking about non-zero vectors. Lambda may be positive. If lambda is positive, that means it's the vector V is maintaining its direction. If lambda is negative, what is the matrix doing to it? It's reversing its direction, right? So for lambda positive, A maintains the direction of V. A maintains the direction of V. If lambda is less than 0, A reverses the direction. Huh? Lambda is allowed to be 0. If lambda is 0, what happens? There is a non-trivial. It means V is in the null space of A. Since V is not 0, it means A is singular. Okay? So a 0 eigenvalue means that the matrix is rank deficient. It has a non-trivial null space. Good question. Okay. Now, with regards to the PageRank matrix, so this, by the way, is the reason that there's this paper. Hopefully next time I'll have before I get my hands chalky, I'll flash an image of both the patent, the original patent for Google, and the paper published in, I think, 2007 or 8, or thereabouts, called the $25 billion eigenvector. This is the $25 billion eigenvector. At least at that time, that's what, according to the paper, the net worth of Google was. It was finding this eigenvector that made Google Google. Okay, so what we're discussing has very, very important real-world applications. And the beautiful part is that we can pretty much learn everything we need to from 2x2 matrices. Now, for that particular example I did, I hope in my notes I still have the eigenvector. For this particular PageRank, for this particular web, what was the, yeah. So let me just write it here. For our PageRank problem, or example, S star was, now we said that the vector represents the fraction of the population at the corresponding node. So we made sure that all the entries sum up to 1. And if I actually solve for the eigenvector, this was 4 over 31, 9 over 31, and 6 over 31. So the first node had the highest score. Now, I don't want to look at all these fractions, because notice if I, in my eigenvector eigenvalue equation, scale the vector v, the same scalar is going to show up on the other side. So they're associated with every eigenvalue is actually an eigenspace. So the eigenspace of lambda is the span of the vector v. Now, sometimes eigenvalues have multiplicities, and I'm not going to worry about those right now. But let's say I have n distinct eigenvalues, then associated with every eigenvalue there's an eigenvector, and the span of each of those vectors is the eigenspace associated with that. So this and the eigenvalue 1 constitute what we call an eigenpair. So in the case of our PageRank matrix, if I don't want to look at this cluttered form of the vector, I can write v as simply just multiply the whole thing by 31. So I'll have 12, 4, 9, and 6. And you can verify for yourself that when I multiply this vector by the connectivity matrix A, I get the same vector back. Okay, so in this one also you can see that the first node has the highest score. So how is it that we can determine these eigenvalues and eigenvectors? So what I'm going to do is start with the two-dimensional story. Look at the 2 by 2 case. And most of what I say will generalize to, if not all of what I say, will generalize to higher dimensions. So I have a matrix A, B, C, D, and I'm trying to figure out if this kind of a relationship holds for this matrix. Can I find a pair, an eigenpair? Does an eigenpair exist? Does an eigenpair lambda v exist such that AV is equal to lambda v? Well, I do what I did in the PageRank problem. In the PageRank problem, I started with this equation, with the equilibrium equation, and I took the AS to one side. Okay, so I'll do the same thing here. I'll write this as lambda I times V, and now I can write lambda I V minus A V equals 0. And on the left, I have lambda I minus A times V equals 0. What does this say about the matrix lambda I minus A? Remember, V, for it to be an eigenvector, it has to be a non-zero vector. Recall, V is not 0. So what does this say? In fact, this relates to the question that I was asked a few minutes ago. Huh? So lambda I minus A must be what kind of a matrix? A singular matrix. Lambda I minus A must be singular, which means its determinant must be 0. So what is the determinant of lambda I minus A? I don't need this anymore. Let's get rid of that. What is the determinant of lambda I minus A? What is lambda I minus A? How do I write it? What's this entry? Okay, so this has shown up in some of the staff meetings as well. I prefer writing lambda I first and then A next. Some of you who've taken Math 54 may have been used to the other way around, A minus lambda I. I don't care which one you write. The net result is the same. I like it in this way because when I write the actual polynomial for the determinant, I have the lambdas showing up as the first term, the highest power of lambda. So I always like it in this way. So what's the top entry? It's lambda minus A. What's this? Negative B. What's this? Negative C. And this is lambda minus D. And what do you know about the determinant of 2 by 2 matrices? What do I have to do? Lambda minus A, it's the product of the diagonal entries, minus what? Minus B times minus C. So this is lambda minus A. I think that part, some of you folks on the other side may not be able to see, so I'll rewrite it here. Minus BC. And what is this polynomial here? Lambda times lambda is lambda squared. Then what? Minus lambda D minus lambda A. Right? So it's minus A plus D lambda. The first powers of lambda are all contained here. Minus lambda D minus lambda A. Minus lambda D minus lambda A. And then what are the constant terms? AD minus BC. Here's the beautiful part. This thing right here has a name. Let's see how much you folks from Math 54 remember. When I add the diagonal entries of a matrix, it's called a trace. of A. And what do we know about this, everybody? Determinant of A. So for 2 by 2 matrices, the determinant of lambda I minus A is equal to lambda squared. Notice the lambda squared showed up first. That's because I wrote this in terms of lambda I minus A. If I had written the A minus lambda, then I would have had some visual clutter. So it's lambda squared minus the trace of A. So the trace of A equals sum of the diagonal elements, no matter what the size of the matrix. As long as it's square, this is how the trace is defined. Okay? So any n by n matrix that you have, if you sum all the diagonal elements, you get the trace. So minus the trace of A times lambda plus the determinant of A. And this has to be 0 because my lambda I minus A must be a singular matrix. It happens if and only if the determinant is 0. So by enforcing that equation up there, I have obtained what we call a characteristic polynomial. And when I put the equality, I have a characteristic equation. And the eigenvalues are the roots of this characteristic equation. So the eigenvalues are the roots of the characteristic equation. I have a quadratic polynomial, so I have 2 roots, lambda 1, lambda 2, in this case. Now let's see how much you remember from high school. Let's do a time warp to high school. Or maybe middle school for some of you geeks out there. In wherever it was, maybe while you were still in diapers, you were studying quadratic equations. And this quadratic equation had 2 roots. What did you learn about the sum of the 2 roots? I love how the geeks just come out of the rat holes. And while you're at it, what was the product of the 2 roots? C over A. Huh? What's our A in this equation? For our characteristic equation, what's A? What's the coefficient of the highest term? What? 1, huh? So from the characteristic equation, so we're done with the high school stuff, at least the review. So this is from high school. Now for us, the highest power coefficient is 1. Instead of x, I have lambda. So what? So what's the sum of the 2 eigenvalues? What's my b? No, it's the negative of the trace. So the sum of the 2 eigenvalues is the negative of the trace of A over 1. So that's the trace of A. The sum of the eigenvalues is the sum of the diagonal entries. This will also be true. So sum, actually I'll just write the general form. This is also true for the n by n matrix. Lambda 1 through lambda n is equal to A11 through A and N, where these, of course, are the diagonal entries. So for a more general case, it's also true, although I haven't shown it, I've only shown it to you for the 2 by 2 case. The sum of the eigenvalues is always the same as the trace of the matrix. What is the product of the eigenvalues? Huh? So lambda 1, lambda 2 is equal to C over, what's my C? The determinant of A. The determinant of any matrix is the product of its eigenvalues. Also true for n by n. So a matrix is singular if and only if at least one of its what is what? If the determinant of A is, go ahead. If one of the eigenvalues, at least one of the eigenvalues is 0, the matrix is singular. So all it takes is for one eigenvalue to be 0, and it would make A singular. Okay. I think I've got enough to do an actual 2 by 2 example. So let's actually do a 2 by 2 example. I've got a set of 2 nodes. You can think of it as a set of websites, pumps, and reservoirs, whatever you like. This is my network. Do you expect, if this had been a PageRank problem, what would you give a score? What would the score be that you would give to each of these nodes? Huh? The score vector would be a 2-dimensional vector, and its entries must sum to 1. So what would the score for each of them be? Half-half. There's no reason to prefer one over the other. So you'd expect the vector 1, 1, or half-half, to be an eigenvector of this matrix, of the matrix, the connectivity matrix for this. What's the connectivity matrix for this system? There's a self loop. So this entry is 1/2, half, half, half. Does this matrix look convertible to you? So what do you expect one of the eigenvalues to be? 0. What do you expect the other eigenvalue to be? If you know 2 by 2 case, you know the trace of the matrix is the sum of the eigenvalues. One of the eigenvalues you've told me is 0 because the matrix is singular. It's got 2 identical rows, 2 identical columns. So what's the other eigenvalue? 1. There's another way to look at it. If I multiply this matrix on the left by the all ones vector, 1, 1, what am I going to pick up? The column sum. Each of the column sums to 1. So that means 1 is, and so if I do this, I get this, because A has unit column sums. Now if I transpose this, I get A transpose times 1 equals 1 times 1. So the number 1 is an eigenvalue of A transpose. And we know that the eigenvalues of A transpose are? How are the eigenvalues of A transpose related to the eigenvalues of A? Why? The eigenvalues of A transpose are the solutions to this characteristic polynomial, no? These are the eigenvals of A transpose. But what do you know about the relationship between lambda I minus A transpose and lambda I minus A? Well, how is this matrix related to this matrix? Isn't this the transpose of this? Am I not looking at that? If I transpose of a sum is the sum of the transposes, and the transpose of the identity is itself. So this is the same as this. And I know that the determinant of anything transpose is the determinant of that thing. And when I set it to 0, it means that A and A transpose have the same eigenvalues. Okay. So we found the two eigenvalues. I need a wristwatch. Can't keep checking. Okay. So A and A transpose have the same eigenvalues. I found the eigenvalues by exploiting this quadratic formula. How do I find the eigenvectors? Well, I plug in each eigenvalue into this expression, and I know that the corresponding eigenvector is in the null space of this matrix. So what is lambda 1 minus A? Lambda 1 is 1. So what is lambda 1 minus A? Lambda 1I minus A. What is this matrix? Isn't it the identity minus this guy? So what is it? 1/2, negative a half, negative a half, and half. So what vector can I multiply this by to get 0? With 2 by 2, you can always eyeball it. What multiple of this column should I add to what multiple of this column to get 0? 1 and 1. Which is precisely consistent with the answer you gave me to the question of what score would you give to each of these nodes? Identical scores. Right? So the score vector for this particular web would be 1/2, 1/2, because I want them to sum to 1. What about V2? What about V2? So I have lambda 2I minus A. Lambda 2 is 0. So I'm looking at minus A. So it's minus 1/2, minus 1/2, minus 1/2, minus 1/2. Right? So what's V2? What linear combination of the columns will give me 0? 1 and negative 1. So lambda 1 equals 1, and the vector V1 equals 1, 1, form an eigenpair, and lambda 2 equals 0, and V2 equals 1 minus 1, form another eigenpair. Now, one other thing I want you to notice is that the matrix A can be written as 1/2, 1, 1, 1, 1, which is 1/2 this product. And remember a few lectures ago I was telling you about a projection onto a vector A? What was the matrix that gave you that projection? It had an expression. It was A transpose A, inverse A transpose. Does this look like a projection matrix to you? And if so, onto what vector? What's this first vector here? What's this first vector here? If A is 1, 1, what's A transpose A? What's the squared length of this? Huh? 2. And that 2 appears in the denominator. That's 2. 2 inverse is 2. A is 1, 1. A transpose is 1, 1 row. So this is a projection matrix onto this vector. Right? So if I'm already along this vector and I apply the projection matrix, what should I do? What should I get? If I'm already in the subspace defined by the span of this vector, I get the same, right? That's why one of the eigenvalues is 1. So this is another interpretation of the same thing. What's the orthogonal vector? What's the vector whose projection is 0? Well, that one. 1 minus 1. That's the vector corresponding to the eigenvalue 0. Okay, we'll pick up next time.